All right, y'all, we are looking right now at the second section of the Topic 10 notes, and we're going to start off with a couple of problems that are not actually printed on your packet. Okay, you can do these on a separate sheet of paper, or you can do them in the margins, but these are going to show up on your Canvas assignment today, so you'll need to definitely know how to do what we're doing right here. Okay, I want to start off with a pretty simple example before we get into this thing right here. I want to start and show you something even simpler than that. Okay, let's say that we were trying to simplify the square root. Excuse me. Let's say we were trying to simplify the square root of 4 times 4. Now you can look at that and do all of the calculation that 4 times 4 is 16, and then come to the conclusion that the square root of 16 is 4. But real quickly, before you even do any of that, you can recognize that you are multiplying two of the same thing underneath this radical. Okay, underneath inside of this square root, you're multiplying two of exactly the same thing. And so what I'm getting at here is that if you have two of the same thing underneath a radical, that is the equivalent of having one of that number outside of the radical. You see what I'm saying? We've got two that are inside of it and one that's outside, and that's equivalent to each other. So when I look at a problem like this, I can see that there are a pair of twos right there, there's another pair of twos, and there's a pair of fives. So what we can do is we can say that having this pair of twos inside the radical is the same thing as having one two outside of the radical. And we've got another pair, so that's the same as having another 2 outside of the radical. And we've got a pair of fives, so that's the same as saying we have a 5 outside of the radical. So all of that we started with is equivalent to 2 times 2 times 5 times the square root of 7. You'll notice that this 7, it does not have a partner underneath this radical. That 7 has to stay there completely by itself. It has to remain inside of the radical because it did not have a partner to come outside with. Okay, doing the quick math, 2 times 2 times 5 turns into 20. So all of that we started with is equivalent to 20 times square root of 7. And if you type that into a calculator, I guarantee you're going to get two of the same exact answer. You're going to get exactly the same decimal answer for each one of those expressions that you would type in. So roll on to this next page. I want to look at simplifying some other radicals. Okay, what we're going to do is we're going to take something that looks like this, and we're going to turn it into something that looks like this. Okay, what we're going to do is we're going to factor the number, and then out of those factors, we are going to find the pairs that match each other, because those pairs are going to show us what numbers will go outside the radical, and whatever's left will stay inside the radical. Take a look at this one right here. Square root of 180. Well, we look at that number 180, and there's a whole bunch of ways that you can multiply two numbers and it be equal to 180. You could do 2 times 90. You could do 4 times 45. You could do 3 times 60. You could do 9 times 20. You could do 6 times 30. There's tons and tons of different ways that you could get there. And let me tell you this right now. It does not matter which one you pick. Okay? Any of those, as long as you continue factoring all the way to the end, will get you the right answer. Okay? So on this one, I selected 2 and 90. Okay? There's no particular reason. I just did. Okay? Any of those combination of numbers will work. So 2 times 90, and then 90 can be split again. Well, that's 2 times 45. 45 can be split again. That's 5 times 9. 9 can be split one more time into 3 times 3. And so what we've just done is we have showed that if we took all these numbers at the bottom of the factor tree, 2 times 2 times 5 times 3 times 3, all of that multiplied together equals 180. And so if that is the case, then the square root of 180 is the same as the square root of all of this stuff all together. Now, what we can see is that we've got a pair of 2's right there, and we've also got a pair of 3's right there. So a 2 and a 3 are going to be out in front of our radical, just like that. We're going to have 2 times 3, but this 5 is going to have to stay inside of the radical. Doing that quick math, 2 times 3, turns into 6. And what that tells us is that this right here, 6 times square root of 5, that is equivalent to the square root of 180. This is the simplified radical version of this number. Okay? Y'all, I'm not the person who invented proper math notation, quote unquote proper math notation. I'm not the person who decided that the square root of 180 is not a good enough answer. But this is part of the expectation now, is that you can go from this to this. Okay? Going from a large number under the radical to a simplified version is part of the expectation now. So let's move on to the next one. Don't shoot the messenger. That's just part of it now. All right. 2100. There's tons of different ways you can multiply and get 2100. You could do 210 times 10. You could do 21 times 100. You could do 3 times 700. You could do 30 times 70. What I picked for this one was 7 times 300. It doesn't matter, again, as long as you end up with two numbers that multiply there. And as long as you factor this all the way out, you will end up with the right answer. Okay, 7 times 300. Well, 7 is a prime number, but 300 can be split into 3 times 100. 3 is prime, but 100 can go again. Well, that's 2 times 50. 50 is 25 times 2, and 25 breaks down one more time to 5 times 5. So when we look across all of this, 7 times 3 times 2 times 2 times 5 times 5, that equals 2100. So again, if we're taking the square root of 2100, it's the square root of all of that stuff being multiplied. And we look for pairs. I see a pair of 5s, just highlighted in blue, and I see a pair of 2s that I'm highlighting in orange right there. All right? What that means is we're going to have a 2 and a 5 being multiplied outside of the radical, but left inside the radical, we're still going to have 7 and 3. So 2 times 5 is on the outside. 7 times 3 is still under the radical. 2 times 5, just doing that quick math, is 10. 7 times 3 is 21. So 10 square root 21. That's our answer for this one. All right. If you have any questions while you're working on simplifying radicals, please let me know. Up next, the next thing that we're going to talk about, the next thing that's on your Canvas assignment, is another kind of special right triangle. Okay. Now on your notes packet, you actually have a picture of an equilateral triangle. That'd be this big one on the outside right here. It's an equilateral triangle, and it's exactly what it sounds like. All three of the sides on the outside are equal length. Okay, equilateral, equal length sides. So, but what happens, what I want you to do and draw on your paper is I want you to drop an altitude from this corner, this vertex up at the top, drop it straight down right here so that it makes a right angle with the bottom side of the equilateral triangle. What you've just done is you have split this equilateral into two congruent right triangles, because both of those would be right angles. You've got two congruent right triangles, and what you did, since you split it in half, you turned this into a 30-degree angle. This angle down here is 60 degrees. And of course, our right angle over here, that's always going to be 90 degrees. And this is where we get the name of a 30, 60, 90 triangle. It's just like the 45, 45, 90. It's got the angles measured, and that's where the name comes from, 30, 60, and 90. Okay, so just like yesterday when we talked about the 45, 45, 90, there is a specific relationship that you can see happening with all of your side lengths in this special right triangle. Okay, first off, you've got a shorter leg on this right triangle, you've got a longer leg on this right triangle, and of course you have the hypotenuse. That's always the longest side. Okay, so the hypotenuse in a 30, 60, 90 triangle is twice as long as the shorter leg, so 2 times the shorter leg, and the long leg of your 30, 60, 90, the long leg is the short leg times the square root of 3. Here's a diagram of what that would look like. Okay, if you've got your 30, 60, 90 triangle, the shortest leg, the opposite side from 30, if that is x, then the hypotenuse is just 2 times x. The longer leg is that x times the square root of 3. All right, so it's just like yesterday, and these problems that we're about to do are also very similar to yesterday. Okay, look at this. It tells us that this is a 30, 60, 90 triangle, and it gives us one of the side lengths. We have to find the other side lengths. So this time it tells us that PT is 4. Well, that would be this side right over here. That's 4. And we know from this previous slide that the hypotenuse is twice as long as the shorter leg. So that's the short leg, and the hypotenuse is twice as much. So PV must be 8. The longer leg, we know, is the short leg times the square root of 3. Well, the short leg is 4, so that means the long leg is 4 times square root of 3. All right, so that one's 8. That one is 4 square root of 3. Go on to our next one. Our next problem has VT labeled this time. Well, VT is the longer leg. Now, the only equation we have that has anything to do with the longer leg is that the long leg equals the short leg times square root of 3. Well, if that is the case, we already have the long leg, right? Long leg equals the short leg times square root of 3. So what's happening to the short leg right here is that it's being multiplied, right? And if we're going to get the short leg by itself, we're going to have to undo that. So we divide by square root of 3. We do that on both sides. On this side, it all goes away. That cancels out. We have x equals 2 divided by square root of 3. That is our short leg. 2 divided by square root of 3. PT. Now, the next thing we're looking for is going to be the hypotenuse, PV. Now, we know that the hypotenuse, according to that formula that we just wrote down a second ago, the hypotenuse is going to be 2 times the shorter leg, right? Well, the shorter leg is 2 over square root of 3. So if we're multiplying, you can treat it like a fraction and put it over 1, and then you can clearly see that you're just going to do top times top and bottom times bottom. 1 times square root of 3 is still just square root of 3. And this also tracks, if you're not even thinking about it in terms of fractions, 4 is twice as much as 2. 2 is half of 4. Whether it has this denominator attached to it or not, that still tracks where that this hypotenuse would be twice as much as the short leg. Go to our last example problem, and then you'll have, and then the assignment is yours to do at your leisure. Okay, PV, this time it gives us the hypotenuse. PV is equal to 3. So we already know that the hypotenuse is 2 times the shorter leg, right? So wouldn't it be fair to say that the short leg is half of the hypotenuse? If this one is twice as much, that means this one is half of it, right? So that means this one is just going to be 1.5. It's going to be half of 3. And we also know that the long leg is the short leg times square root of 3. So all we've got is 1.5 times the square root of 3. Not what I was intending to do. There we go. All right. That's all we've got for these notes. Y'all have a good day and get to work on that Canvas assignment.